All right. So my last slide here, I say, what is a hard drive? What were we talking about at the end? Whoa. um, well, I remember from this slide we were talking about like what if we were having to create the thing for Dropbox? Oh, I'm with us now. He came back. So if we were having to support Dropbox in terms of storage, realistically speaking, they're buying the same hard drives and stuff like that that we can buy from Best Buy or Newegg or whatever. They're buying probably the more expensive ones. Like if you go into Best Buy, um, and let's say you're looking at external hard drives, Western Digital drives. You know how they have like the three different ones and they're like same capacity, but some are more expensive than others, right? What's the difference between them? They have like the green one. Here, let's actually bring that. Best Buy is a direct USB hard drive. Western Digital external. Okay, so like here we have like silver and black.
Yeah, what is that their own personal cloud? Is that just like a big?
It hooks into your network at your house. So instead of into a computer, it gives you like a drive, a network drive.
Okay.
Ooh, 4 GB coming soon, or 4 TB rather.
Yes.
Yes. Sick. Oh, come on. Show me some things that are like actually available. Sort by. Let's go best selling. I might not be able to give you a great example here. Oh well, doesn't matter. But you've probably seen it where they have the external hard drive, like Home Edition, usually is kind of in a green box or something like that, and that costs X. And then they have the same capacity drive that might be the Pro version or something like that, and it's like $30 more. And then they might have one more level up that's like $15 more or something like that. Same capacity drive. What things are different between those drives? What are the variables that play into a hard drive? What makes one drive different than another one besides capacity?
Read-write speed.
Okay, read-write speed, and that's usually tied directly to what? I don't disagree, but that's more of the evidence than the feature. So it's usually RPM, at least in a mechanical drive. That goes out the window when we start dealing with solid state. But RPM, so common RPMs are 4,200, 5,400, 7,200, 10,000, 15,000. That's ish. And 4,200, you'd only see this on like budget pleaser laptops. If you have a desktop computer with a 4,200 RPM hard drive in it, run. Somebody's ripping you up. They don't, because I think they only make those in laptop size hard drives. Okay, so I would say you're common, and I think I brought this example up one other time where sometimes you're online, like at Dell or Apple, and you're configuring a machine, and you could have a 1 TB drive that maybe is stock, or you can drop to a 768 GB drive and add $100. So less capacity, but more expensive. Usually that's because it's a higher performance drive. It's a 7,200 RPM instead of a 5,400 RPM. something like that. So that's going to translate directly into read-write speed. Okay, what else is the difference between a hard drive? Let's talk about external hard drives, since we've already sort of had this conversation with internal drives. So we're talking about external hard drives. What else drives price? So what's the difference between that economy or home edition and the pro edition?
Color.
Potentially color. Well, here, let me ask you, why do you buy an external drive rather than an internal drive? What's the advantage of an external drive? Portable. You don't have to open up your computer, yank it out, and then go and find another computer that you could put it into. You have to open it up. So, external drives are beneficial. You give up some performance, right? Why? The interstate between the hard drive and you're not dealing necessarily with serial ATA. You're dealing with USB or FireWire or something like that. So you give up some performance potentially, but you gain flexibility, portability. Okay, so what's the difference between those? What's another difference between those different quality hard drives, those different external drives? You might have speed difference. Internally, one might be 5,400 RPMs. Maybe the more expensive ones have 7,200 RPMs. A little bit better hardware inside. Realistically, inside is the same hard drives you would buy to put it in, inside your computer. They just put them in a external plastic case. So what else is the difference? How many of you have ever bought an external USB hard drive? How many of you ever stolen it? I don't know how far this rabbit hole goes. I mean, you can still MP3s and file. I mean, you guys go into Best Buy with the winter coat? No comment. Ooh, that coffee's gone bad. Or the cream, rather. Ooh. I will. It's only a little off. It's one of those things where it's kind of like eating yogurt at this point. It's good bacteria. What does not kill you makes you stronger. I have a complaint before we continue on. I saw Ender's Game on Saturday. The movie. No, it was good as a movie, but if you read the books, you'd leave the movie very disappointed.
Isn't that kind of like the same for every single movie?
No, and I agree with that. I think this is worse. Like the movie had a very, very different tone than the book. It didn't seem like it, even though it was the same story, it didn't seem like it was the same story. It was just such a different tone. And even opportunities where they could do the same thing as the book. Like one of the scenes dealt with a fight Ender has with some kid. And in the book, this was like a big, long, drawn-out thing that ended up with this fight with two boys in a shower. Steamy. But in any case, they built it up to the point where you could have had the fight happen just like it did in the book. Yet they chose not to. They chose to have the fight end differently. I mean, it was just like stupid. Yeah, it was.
I don't know if they're going to show two boys in the shower.
Well, no, it was literally a fist fight. They were just trying to corner him, catch him when he's alone in the shower, all soaped up. So I was disappointed in the movie. I'd give it maybe like a 6 out of 10. It was an entertaining enough thing for a movie. Like if you hadn't read the books, you'd be like, oh, that's kind of a neat premise, but they just purposely changed details that didn't need to be changed. You understand that they're going to leave things out because you're trying to squeeze it into a 2-hour movie, but the things you leave in at least get accurate. And they didn't. I was upset. All right, so when you buy an external hard drive, what drives that price? Maybe RPMs, capacity, but now we're dealing with, let's say you have two drives, same capacity, both 2 terabyte, same RPM, let's say they're 7,200 RPM drives, but one's more expensive than the other. Why might it be that? What's the driving force there? Well, clearly when you buy an external hard drive, what things do you care about? What things do you look at? So after you're looking at two 2 terabyte drives.
Price.
Well, now you might look at price, but what are you giving up? Let's say one of them's $30 more than the other. Same manufacturer, same speed, same capacity. Why might you pay $30 more for one than the other? Oh God, it's nasty. Why do you keep going back? I have to know. This is like all curdled on top. Give me a second. No, there's not like milk solids. It's probably okay, man.
Drinking a case of chunks. Chew your coffee.
So when you buy an external drive, let's say we're just talking about USB. Are all USBs created equal? Is USB USB? Well, the original USB, all USB plugs look the same, right?
Yep.
Okay, but they're not all the same. You have USB 1, which was the original USB. Nobody uses that anymore. How fast was the original USB? So we're back to we're talking about interstates again. USB 1. How fast was that? Are you just Googling it?
Yep.
Tell me how fast you think it was.
Not that fast.
Original USB was 11 megabit per second shared. Okay, well, what does that mean? Well, in order to even talk about USB, we need to talk about something else. Serial versus parallel. You heard of serial and parallel? So this goes back. We have a historical sense for this, but then it still has a modern, there's a modern competition. How many of you remember the printers that had the big fat cable thing that fit into the back of the printer, and then it went to the back of your computer? It was the giant, it was called the parallel port. Printer plugged into the parallel port. And then you had, how many of you ever had a dial-up modem? An external dial-up modem, I guess. Okay, external dial-up modems, they had a cable that went to it, and it went into a smaller plug that kind of looked like a VGA, a video connector, but it was like the female version of that. So it was the other side. That was a different cable. That was a serial cable plugging into a serial port. Sometimes they're just called COM ports. Well, what's the difference between serial and parallel? Serial is one bit after another in linear formation. So it's just a line of bits. Parallel is usually 8-bit chunks. So 8 bits at a time, or 1 byte at a time. Well, which is better? Huh? Well, maybe on the surface, parallel seems better. That's always the answer. Whenever somebody says, with technology specifically, but probably almost anything, which is better, it always comes down to it depends. What's the advantage of sending things 8 bits at a time versus 1 bit at a time?
Probably faster if you have a big amount of bits to send.
It's sending things out in 8-bit bursts, right? So you're getting more information out onto the highway, at one time. Now, what happens with an interstate when you get too much information on it at once? Gets backed up, right? Yeah, you get a data jam. Possibly car accidents, things bumping into each other, so possibly bad data, things like that. Okay, but certainly if you have 8 entrance lanes onto the interstate, you can get cars onto that interstate more quickly than you can if you have 1 entrance lane on the interstate, right? This makes sense. So you have a big packed interstate. Let's just say from Mequon down to Milwaukee. You know, we have for most of that you have 3 lanes. Let's say it's rush hour, which is nothing like rush hour in a bigger city, but Milwaukee has legitimate rush hour compared to like most normal places. So you have 3 lanes of traffic, and let's say they're all backed up right around 7:45, 7:50 in the morning. Everybody's on their way to work. How much slower? Sometimes you see those signs, right? Like this is how long it'll take to get to this exit or something like that. So you're kind of stop and go, stop and go. Now what if there was only 1 lane? Would it necessarily be slower? What's some reason for traffic backups? So why is rush hour, why is it automatically slower? I mean, it seems like everybody's trying to get to work, so it's not like people are putzing around. What are the reasons that it makes it slower?
So many cars in one area.
Okay. Certainly part of it. Wouldn't you agree it probably has a lot to do with cars leaving and, more importantly, entering the interstate? Because that clogs up 1 lane where people have to start getting over, and that's why you see the biggest congestion usually around exit and entrance ramps. You know, then you have that a pathway where everything's moving fine until it slows down again, right? So when you have that many lanes that people are coming on or off, it backs it up. Now, what if we just had 1 line of traffic? 1 line of traffic. Do you necessarily think that it would take longer to get to your destination? Or might it take about the same amount of time to get to your destination? It just might happen that the experience might be a little different. You know, because when you get to those you know, the entrance thing, a car might slow down to let another car in and then keeps going, as opposed to having 2 lanes of traffic trying to merge over so these cars can get over that maybe back it up even more. So parallel version of interstates are bursty. You can be going really, really, really quickly and then all of a sudden have to slow down as certain things are happening. Then you get going quickly again, then you slow down. Where if you had 1 big long line of cars, chances are you're never going to get to the point where you're going ridiculously quick. But you might be able to just kind of sustain a speed. Does that make sense? You know, I'm trying to drag it into automobiles or something like that, so it's a little bit forced. But I mean, I think that there could be some truth to that. Maybe if you have 1 lane of traffic, you never actually get up to as fast of a speed as you did with 3 lanes of traffic, but maybe the ultimate time that you spent in transit might be close to the same. Just because you had a consistent speed rather than starting and stopping, something like that. Okay? So we had serial versus parallel. But from our perspective, the difference between these guys is one's 1 lane of traffic, another one's 8 lanes of traffic. Something like that. Okay? Then we had USB FireWire. What's the difference between USB and FireWire? How many of you just assume they're just kind of competing technologies that do the same thing? Well, I don't think that's an unfair statement. I mean, they accomplish a similar thing, but the way they accomplish it is different. USB is a parallel technology. FireWire is a serial technology. I'll jump back here in a second. USB 1.0 had a maximum speed of 11 megabit per second. USB 2.0, and this was shared. When USB was first introduced, one of the big factors was you can daisy chain up to 128 USB devices together. But it still shares all that speed. And USB also has power that runs over it, so you can power devices. But so it's a highway that can have 11 megabits of data traveling on in any point in time, and it happens in parallel. USB 2 I want to say it was like 200 megabit per second. Actually, it was more than that. It was more than that. It was like 800 megabit per second. And then USB 3 is something like, let's just say 2 gigabit per second. I'm probably losing some accuracy there, but let's just say that's roughly what it is. But all these are in parallel. Firewire one point oh was 400 megabits per second, and that came out at the same time as USB 2. Let's just say ish. And 2.0, which is the latest one, I think is, let's just say 1 gigabit per second, because it's slower than USB 3. Okay. So in any case, actually, I want to say it was like 800. I want to say it was actually like that. So if you could have a USB 2.0 hard drive versus a FireWire 1.0 hard drive, which would be better? Well, FireWire is 400 megabit per second. USB 2 is 800 megabit per second, twice as fast. It seems like the obvious answer is USB 2. Well, it depends. When would USB be the preferred technology? Forget about the speed for a second. Sometimes the speed might be fast, so much faster that it makes up for any weaknesses. But in this particular case, we're talking 400 megabit per second versus 800 megabit per second. Both of them are pretty fast. What would be an example where USB technology would be preferred? The whole stop and go thing. So go back to our interstate example. My argument is that the USB version of our hard drive, the parallel version of our hard drive of our interstates, you're going to do a lot of start and stopping, but you have bursts of speed. Whereas the serial version of our interstate, you basically have a consistent speed. So ultimately, you end up at your destination in about the same amount of time or in a reasonable amount of time, but you don't have all that starting and stopping, but you never get going as fast as you ever get going in the parallel version of the interstate. So with that in mind, it's fair to say that USB is bursty. We have bursts of speed. FireWire has a more consistent speed. Where would bursts of speed be acceptable? And maybe the second question is when would consistent speed be preferable? Go ahead.
Doesn't USB slow down a lot when it deals with pictures?
Um,
That's my imagination.
I would say not necessarily,
I've
but
always noticed that it kind of like goes through file by file, and also gets to a picture, not a crazy size picture, but it just slows down.
it could be. There could be something with how the driver's written or something like that. But I'm talking more big picture technology. Like, why is USB, the bursty aspect of USB, when is that bad versus when is that good? Versus FireWire being more consistent speed, even if it's slower burst, slower, even if the average speed is slower, if it's consistent speed, when would that benefit us? What are things you use your hard drive for? Well, one might just be a gigantic data storage, right? If you're copying a terabyte of files onto a hard drive, do you care about the burstiness? Or the start and stopping? You're okay, you're gonna just copy it and move away, right? So in that case, USB is fine. If your average speed is gonna be faster, you'll copy it faster than you would on an equivalent FireWire drive. Especially over an hour of copying or something like that. Well, what's an example of technology that we might use that would benefit from consistency? There's really one glaring example, and that's video editing. So when you think about video is a whole bunch of still images displayed in a row. So if we're doing a video capture, it's very important that we receive those images and capture them and compress them at a very solid cadence. Not a whole bunch really quick and then a slowdown, and a whole bunch of really quick, then a slowdown. That's when you start getting choppy video. So real-time capture of video, which is a common thing, will produce a better quality product over a FireWire type connection than it will over a USB style connection, because USB is bursty, where FireWire is not. And that's because one is serial and one is parallel. USB is parallel, FireWire is serial. That make sense? So different hard drive interfaces. How many of you have heard of IDE hard drives? A little bit older, but if you ever looked inside of a computer, you had those the flat gray ribbon cables. You know what I'm talking about? Those are IDE cables. So on the end of it, it has like a connector. It's about that long, and the back of the hard drive has, you know, I don't know, what is it, 64 pins or something you plug it into. So that's IDE. IDE is a parallel technology. In fact, when you were working with IDE hard drives, they would actually talk about burst rate. So again, it's a parallel technology. SCSI, how many of you have heard of SCSI before? Usually you talk about SCSI in the server industry. Small computer system integration is what SCSI stands for. But this was a serial technology. Huh?
Small computer.
System integration. And nobody knows that, by the way. When we interviewed for IT positions at Western Illinois University, it used to be one of our joke questions we'd ask. It's not important that you know what it means, what it stands for. Nobody knew what it stood for. Just that happens to be what it stands for. What we were really looking for is, do you understand the difference between SCSI and IDE? In practice, IDE, being a parallel technology, allowed you to daisy chain two hard drives together. SCSI would allow you to have more. SCSI actually worked a lot like the early Ethernet, the T-adapter Ethernet, where you had like an endpoint that it just bounced off of it. Screaming out in the hall, crazy man down there. Okay, so in any case, we have serial ATA. Which technology is that? Serial ATA. That's a serial technology. Okay. So out of ID and SCSI, the serial technology ended up coming out ahead. For years, you had SCSI was what you'd use for servers. ID is what you used for home computers. You got better average performance through a serial communication. Somewhere in the middle here, we had something called fiber channel. And those were really expensive. Those were only servers, fiber channel drives. So serial ATA is what we use today. That's kind of like the best of both worlds, but it's a serial technology. Okay, so getting back to what's the difference in those hard drives that we have the same capacity, the same RPM. Usually it's number of connectors. So the cheap drive might be USB only. A more expensive drive might have USB FireWire. An even more expensive drive might have USB FireWire. This is not even formatted in anything reasonable. FireWire and serial ATA, external serial ATA. So you can get a single drive. So it's an external drive now, but if you have an external serial ATA port in your computer, you can actually have internal speeds with an external drive. with a drive that supports a serial ATA interface. That makes sense? And then some drives might actually also have Ethernet on them for that cloud storage type thing. Some might even have Wi-Fi. So the more expensive drive at the same speed and the same capacity usually has to do with the number of ways that you can interface to that drive. Does that kind of make sense? So that's what you're looking for. Those are the things that drive price when you're at Best Buy looking at some different drives. So now getting back up here to the cloud. So if you're Dropbox, you're buying the same hard drives as everybody else bought, right? You know, maybe you are buying for your internal drives, you're buying the ones that have faster RPMs and, you know, higher capacity, whatever it is. But you're buying a whole bunch of these. So the question we were talking about is, if you had to describe a hard drive in terms of a data structure, what might you say? What does a hard drive internally look like? Hard drive stores things, right? Think of a hard drive kind of like a shoe bench or something, where it just has a whole bunch of individual pockets. And each of those pockets can hold something. Just a zillion unnamed variables. So a hard drive works a lot like an array. So what's an array? If you had to concisely define what an array in a programming language is, what would you say? Oh, it's so disgusting. Oh, I can taste the
Where did
film.
you get that coffee from?
The cafeteria? It's not the
Oh.
coffee. It's the creamer, I think, that I put in it. I think the creamer was questionable. It would just be hilarious. I'm just up here. It's like he just kept drinking bad coffee. I just started throwing up all over the place. Like, answer the question. What's an array? Like, I couldn't even make eye contact anymore. It was he didn't even lose a beat. What's wrong with him? What is an array? An array would be a single variable name that allows us to store a whole bunch of pieces of information, right? Okay. So we have our hard drive, and inside of our hard drive, we can store a whole bunch of individual pieces of information, right? How do I access the individual pieces of information of an array?
By buckets.
Yeah, they're separated in a bunch of buckets. So I go to bucket 0, there's some information there. I go to bucket 1, there's some information there. What information is at bucket 0, at bucket 1? Who remembers that? We're the programmer. We probably know what's at what bucket, right? Now, we have an issue though. Arrays and hard drives are different in that arrays only exist as long as our program is running. As soon as our program ends, our array disappears and all the memory associated with it disappears, right? But with a hard drive, when you turn your computer off, do you expect your data to still be there when you turn it back on? I like to keep my expectations low. That way I'm always pleasantly surprised. Okay? We want it to still be there. That's where a file system comes in. Our hard drives are already built to have a whole bunch of buckets, a whole bunch of chunks of memory where we can store things. Okay? The means by which things are stored that's more the mechanical side of the hard drive, whatever. Fine, but from our perspective, think of a hard drive as a gigantic array. All right? Now, when we think about our file system, one of the jobs of that file system has to be keeping track of what is stored in your hard drive and where. Make sense? How many buckets of memory does a hard drive have? Let's talk about in a worst case. So now we're talking about the difference between the hardware and the software. Again, this goes back to, we're looking at a microcosm of operating systems in general. Because remember back at the very beginning, what's an operating system? It's a piece of software that sits between the human being and the hardware. So if we're talking about a hard drive from a hardware perspective, what is the most number of storage containers that a 2 terabyte hard drive could have? Give me the theoretical maximum number of containers that a 2 terabyte hard drive could have. It's not a trick question. What's the smallest thing that we can store inside of a computer? 1 bit. 1 bit. So if we literally allowed our hard drive to store things in 1 bit chunks, the most number of
That's a lot.
a lot of buckets, right? Okay, so 2 terabytes would be a big, big number. It would be 2 times 1024 times 1024 times 1024 times 1024 times 8. So big number, right? It's huge. It's a huge number.
2.2 trillion.
Okay, huge number. That's how many individual bits we can store. Why don't we store? I mean, how many of you think our hard drives are written that way? Now you said 2.2 trillion, right? Actually, I think it's bigger than that.
Like we
So we're going to say 2 terabytes times 1024 is gigabytes times 1024 is megabytes times 1024 is kilobytes times 8. Well, no, wait. Times 1024 is bytes times 8 is bits. So that's 1,000.
Thing is worse. 8
Okay, so that's 44,186,590. No, it's 17 trillion.
They gave us bytes.
Okay,
They called it bits.
I got you. 17 trillion, but huge number, right? Okay, that is the number of buckets. If we have a hard drive, a 2 terabyte hard drive, that can each hold one, and each bucket of the hard drive can hold 1 bit. The number of buckets we have is this number. Giant number, right? What's the problem with that? When we think about an array in Java, what's the biggest array you could create in Java? What would you suspect the biggest array you can create in Java is? When we create an array in Java, we usually do something like in array AR is equal to new in array, and then we give it a number, right? Like 100. That creates a 100 bucket integer array. How big of a number can I put in here? Maybe size of int would be a decent guess. Maybe they've implemented it as unsigned, but probably not. So probably the biggest I can store is 2 billion. Maybe it's 4 billion. Maybe. So a lot less than what we need to store for our 2 terabyte hard drive. Each bucket's a bit. How big is an int? Let's just go off of this idea that it's the size of int. An int is 32 bits. Well, what's a 32-bit operating system? We heard phrases like that before? It's a 32-bit operating system, or it's a 64-bit operating system. 32-bit OS typically references the OS is built around a 32-bit int, which basically says we use 32-bit integers for counting stuff in our operating system, which means the maximum number of buckets that we can represent in our hard drive that our file system could access, uniquely index, that's the better way of saying it. The number of buckets that we can uniquely index in a hard drive is 4 billion. 4 billion buckets. Well, if I have a 2 terabyte hard drive, well, we need to look at this. This is our number of bits. Let's divide that by 4,000,000, 40,000,000, 400,000,000, 4,000,000,000. Each bucket we could hold 4,398 bits. Divided by 8 is bytes. Divided by 1,024 is kilobytes. So half a kilobyte would be the maximum for a 2 terabyte drive. We're probably not holding a half a K per bucket. We're probably holding something like 64 bytes or something like that. You know, something significantly smaller, but much, much, much bigger than a bit. Make sense? So maybe something like 256 bits per bucket might be and could even be like 4 megabytes per bucket. This is only if we were dealing with a 2 terabyte drive. Now, doesn't seem like a huge deal. That would be in a 32-bit operating system. What about a 64-bit operating system? We can index more buckets. Okay. Usually hard drives refer to this as their block size. Block size is size of bucket in hard drive. Very, very similar to when we talked about paging memory management where we had the page size or the frame size. Block size is like the frame size when we're talking about hard drives. But now, let's go back to this slide. We have 65,000 3 terabyte hard drives. Size of int ain't gonna cut it. Right? About 64 bits. We have an issue. Okay, we have an issue. Because now, one of the jobs of the file system is to keep track of everything. But now I have so many drives that this file system has to span that how can I keep track of everything? How do you solve this problem? You know, we talked about RAIDs, where we treat our storage as one gigantic hard drive. And then last time I think we looked at some of these pieces of equipment that kind of, in hardware, daisy chain a bunch of drives together, right? So it's as if you have 200 drives in a single machine or something like that. And they just concatenate those drives and then somehow behind the scenes have backup stuff or whatever. I mean, they are meant for this problem. They are specifically built pieces of equipment to allow you to store, they're called storage arrays, allow you to store a whole bunch of data across a bunch of individual physical drives in such a way that from the end user's perspective, it's one gigantic storage array. But somewhere we need to be able to keep track of which drive each of those things is stored on. How do you solve this problem? Hopefully we're already starting to see some patterns where memory versus hard drives, the solution to the problem is fairly similar, isn't it? I mean, kind of what I'm talking about here, isn't this kind of a paging memory management scheme for hard drives? Fairly similar thing. The hard drive is split up into a whole bunch of equal size buckets rather than storing an entire file in a bunch of storage space and then another file that's a different size and a bunch of storage space. Now we're going to split our files up. Just like we split up, you know, we talked about the page data structure, keeping, you know, what page number it is. Now we're talking about the block data structure. Pretty similar thing. It's going to hold data that's long-term data. What makes it long-term? The fact that how your hard drive works makes it long-term. So writing to a hard drive, a block to a hard drive is very similar to writing a page to memory, except the equipment we're writing to, one of them is static, where, you know, once the electricity turns off in RAM, anything that's in there falls to the ground. With your hard drive, it Just stays in there. It's the nature of the equipment. But now we have this gigantic storage array with, terabytes and terabytes, thousands of terabytes of hard drive space split up across a whole bunch of different pieces of equipment. It seems unlikely that our file system is going to be based on a 5 or 6 terabit integer or something like that, so that we can index all of the individual buckets. That seems to be unlikely, because the math would start getting very big. You try counting up that high. So how do you suspect, again, the hint here is the pattern. How do you suspect those storage arrays probably work? Somewhere we're going to have kind of a master file or master file system data store that's going to keep track of where each piece of data is. So if we have 1,000 hard drives, and each of those hard drives has 100,000 blocks, just use that as the example. How do you address where a particular piece of information is stored? 2 numbers, right? We have the index of the hard drive. Maybe it's hard drive 8, and then it's storage block 513. So it's an abstraction of file system on a single hard drive. We're just keeping track of two indices. Instead of one gigantic unique indice, we make it unique by keeping track of 2 numbers. What hard drive? What position on that hard drive? So it's a file system of file systems. Do you think that each of those hard drives is probably formatted as NTFS or something like that? Each one has a normal hard drive format, right? So the drive in and of itself knows what it's storing. Because what's the job? The job of that file system is to keep track of what's on that hard drive. That's the job of the file system. We haven't even talked about it communicating with the operating system yet. The job of the file system is to keep track of what's on that hard drive. Now, that storage array in and of itself is going to have its own, let's call it pseudo file system. It works a little differently because now you're addressing, you're basically storing a collection of hard drives. Where is this user's data stored? It's on these 9 hard drives or something like that. And then you drop down into each of those hard drives to find out where specific data is. That make sense? And with something like that, we can build the problem up to basically infinite amount of storage. How many hard drives can we have in our storage array? Size of int or size of long, right? But then we might run into that same problem. We're counting too much. So what do you see in those pictures we looked at last time? Last time we had a storage array cabinet had, let's just say it had a block for 100 hard drives. And then what can you do? You can get multiple storage array cabinets and hook those together. So now it's a 3-tier problem. Each cabinet has 100 hard drives in it. Each of those hard drives knows what files are on themselves. The cabinet itself keeps track of its 100 hard drives and what stuff is on those 100 hard drives in terms of big picture. Then you connect all the cabinets together, so you have a file system that governs the cabinets. Which cabinet is certain piece of information on? This kind of makes sense? So what's the maximum number of cabinets you can have? Maybe it's size of int, maybe it's size of long. Keep building the problem up, right? Okay. But the punchline there is there's patterns. We're solving the same problem over and over again, and we just keep wrapping it in a new garbage bag. Kind of make sense? So hard drive file systems, memory management, all the same crap. It's all the same crap. What's up? I got 1 more minute. Well, we're legit. Now I don't have a minute left. I'm done. You took up my last minute. Okay. I will very likely have a homework assignment for you on Wednesday.
Oh, man.
We haven't had a homework assignment here for a while. Oh, hopefully a long one.
Come on, man.
You want a paper or you want a program? Carrie just rolled her eyes at you. I saw it happen.
Me?
No, Dane.
I thought you were looking at me. What did I do?
All right. I'll see everybody on whatever day it is.
Not Wednesday.
Wow. Oh, yeah.
Just shut up.